So we are back to chapter 3, as I said, and we are going to speak about more advanced features that you need to know in order to really master what is going on. So the first main feature is the fact that the geometrical objects, they are part of a homemade plant library, geometric object for which most of them, some of them have been made specially for plants, and that is called the Plunger library, and that is initially coded in C++. And this is the library, the geometric library that is used when you are at the O command to draw a sphere, or the F that is drawn as a cylinder. There is this library that is called the swung. It's also this library. What you need to know, we don't go into the details, but this library can be attacked directly, not within LPy, but within a Python program, because there is a Python API, application interface, programming interface. And you can create your cylinder, give it a material, create a shape, create a sphere, translate the sphere, etc. And in the end, you add your first shape to the scene that you created here. You add another shape to the scene, and then you view, and then you get the final result. And you can combine the elements in any way you want in this way. So the Plunger library comes as it comes as a sort of hierarchy of objects with simple objects that are in the primitive hierarchy, with simple things like boxes or cones, and more complex objects like asymmetric codes, extruded hull, extrusion. So the swept surfaces, and all this are in this part. Then you can transform the primitives using a number of transformations, like rotation, translation, and this type of thing. And then you can group this object to make up a hierarchy of objects. So this, nothing very special. Just the fact that there are specific primitives that have been designed to be at ease with the design of plant organs, such as the swung, etc. So this we already saw. There is a way to directly call this geometric primitive from LPy, as I said. So F would be the cylinder, O would be the sphere, and to produce a generalized cylinder, which is a cylinder that has not a straight nerve, a straight axis, and that for which you can scale the radius. Then you would have a primitive that is called @gc. You can have a sweep. You can set the color. You can have swungs. I didn't mention this here. And if you want to call any type of PlantGL primitive with its name, you just use the primitive @g, small g, and you can create any type of primitive that is in the library. So for some of them, they are reserved names, but for every of them, you have the generic @g primitive. So you can have this in Python. For instance, you could say, I want to call the cylinder primitive from the PlantGL library with the certain number of parameters, the radius and the length. And then I call the sphere from the PlantGL library, and this would be equivalent to this in the PlantGL language without using the @g. Okay? So you see that the LPy is a more compact way of expressing things. You have examples that you can use if you want to check this out. Okay, now, what is very important, and this is what I was starting to explain just before, is that while you have a derivation that is made from the axiom to further derived lstring, so you apply the rules P, but things are more complex behind your back, and each time you apply a rule, before applying the rule, a function is called, which is called start each. So you will have the start each before each time. after the function is the function has returned the lstring, and each function will be called, and again and again and again up to the end of the simulation. At the beginning of the simulation, the special function start is called, and at the end of the simulation, the special function end is called. So this makes it possible for the user to have entry point to modify the lstrings at each moment. And this is very important here. This is very important if you want to act on the lstring while the computation is proceeding. For instance, I would like to take into account external events occurring in the world. I don't know, I have light. Light is changing. I want to compute the amount of light that falls on my plant. How I do this? Because the light is not in the lstring. The lstring is the plant. So for this, I need to maintain, in parallel of this simulation, I need to maintain the simulation of the light, how the light would be moving, this type of stuff. And then once at stage K, I would look at the result at stage K, compute my light, to find a way to express that the light is impacting the plant, and this would be done here in this endage, where two things are given to the user, the lstring, so this one, and the lscene, which is the one that is computed after the interpretation rules. Okay? So here I have both, at this point, I have both, so in this function, I have my lstring and I have the geometry of this lstring. So I know exactly where are the components, everything. So I can act on this and make some computation and I can modify the lstring, so this is here. This wk is modified into wk prime by my action. And here I instructed the lstring to have more light, to have a certain light on the leaves, for instance. Okay? Question on this? It is just for you to know that there is a mechanism that is precise and detailed in the LPy functioning, where you can interact with the system during the simulation from the outside. Okay? If you want to have a bit of access to your lstring, okay, because I said that the system is computing lstring, but you may want to know what is inside your lstring in a quantitative manner, not only in the graphical manner. You need to have ways to access to the lstring. So the lstring, you can think of it of a list. It's a list of modules, exactly as a Python list. So if I want to access to the kth module, I just say, so there is a global variable that contains the lstring, and it's called lstring. So you can type at any moment of your simulation when you have you can type lstring, and you will see the current stage of the lstring. So if you type lstring of 0 or lstring of k, 10, you would get the kth module of the lstring. This module can be also the bracket, the open bracket. Okay? So if I have something like this, if I have a of x, of 0, b of 1, square bracket a of 2, c of 3, f of 1, okay? So this would be lstring of 0. This would be lstring of 1. This would be, lstring, of 3, of 2. This one would be lstring of square bracket here, of 3, and so on. So you see that this bracket counts as a module because it is interpreted by the turtle as an entity. Okay, the name here, this one, the label of the module, you can access it with the name. It would be similar to say lstring. I abbreviate the whole lstring by ls. Okay. To say lstring of 2, for instance, which would be not 2, 1. lstring of 1, which would be b of 1, dot name would be the same thing as writing lstring of 1, 0, which is would be the first attribute of the lstring 0. Okay. If you have attributes, like for instance, you can access the attributes by lstring of 1 and with a certain attribute which would correspond to the range of the attribute in the attribute list. Okay, and then you can add argument exactly as in a list by using the primitive append, and you can get the length of the lstring by using the primitive length. Okay, so all the things that you can do with a list, you can do with the lstring. And it's especially nice to retrieve the name of the modules, the attributes of the modules from the outside. Because if I want to act on the lstring, I need to know how to read the lstring and then to feedback the lstring with arguments that I may have computed outside. Okay? So basically how this is used, it is used here. In the end-each function, I get the lstring, the current lstring. I get the current lscene. And here, if I want, I can look at the lstring within the Python script. So for instance, if the string is b and a with 2 parameters, I can retrieve everything. For instance, here, I can take the name of the first module, which would be A. This is the zeroth module. This is the first module. So first module would be A, and the name would be A. The length of the lstring is 2, because there are 2 modules. The lstring, the first parameter of the lstring 0 is 1.2. What else? I can use, because I declared the module as being a time and a radius, I can use also the time and the radius in full script, in full letters, to refer to the value of the things, and so on. Okay? Okay, and I can even modify the argument. So, for instance, here, it is the way I would put backlight computation to the lstring, for instance, I would have leaf with parameter light, and I will compute the light outside and say, okay, the amount of light that is coming on this leaf is such, and I would put back this amount of light in the lstring so that the lstring can continue and take this amount of light to make decisions. Okay? The lstring is not only a list, it's also a tree, because there are brackets, remember? And there are primitives. So all the primitives that you can use on the lstring are here. You can have them very easily by using the help function, function in the help primitive of the Python language. You tap lstring dot, and then you tab or whatever. And then you get all the things, and you see that there are keywords like parent. And parent means that in my tree, so the lstring is a tree, and for each module there will be a parent module, except for the root. So if I call parent on like lstring parent of the ith module, I will get the parent of I. If I call the children of I will get the list of children of I. And in this case, maybe it might be useful for you, Jeanne. You may reconstruct from outside of the simulation of LPy. You could reconstruct the tree and then make your own algorithm outside on the tree, and then feed back the values in the tree that you return from your external module. Okay? So here, for instance, just by using this, so I browse the lstring, okay? And for each element of the lstring, I just give the list of parent and children, which means that I'm able to reproduce the tree of the lstring. If I want to build a tree, I could use this very easily. Okay, again, you have examples that explain a bit this, and that you can look at afterwards. And the last point, manipulation of lstrings from the and-each functions, is that you can manipulate also the lscene as well. You can, and this is important when you want to access the geometry of the different objects. And the lscene is a list also, and it is made of shapes. And each shape of the lscene is made of 3 elements, which is the geometry, which is a Plunger geometry primitive, an appearance, which is basically the color or the texture or something like this, and an ID that makes the mapping between the lscene and the lstring. So this is extremely important. It works like this. If I have a lstring and I computed a geometric interpretation with the interpretation rules. So this is the lstring, and this is what I see on the screen after its geometric interpretation. You see that because of the geometric interpretation, it may be that I have a one-to-one correspondence sometimes, like an internode is made by a cylinder. In fact, it's represented as a cylinder. Internode is represented as a cylinder. And sometimes you see that one single symbol in the lstring might lead to several symbols in the several geometric primitives. So you need to have this mapping here to say that the green comes from the A and the red comes from the A. So this mapping makes it possible to track the IDs of the lstring from the lscene. So if I want to scan the lscene, for instance, to check the geometry of my object, make some computation of the geometry, like the leaf. I have a leaf. Start to be red. I will write in brown. So I have, let's say, a f, then a leaf of x, then a f, etc. This is my lstring. Okay, and the leaf is interpreted as pethiol and also a blade. Okay, so I will have this and a leaf for each leaf here. So the index, the leaf, so this is the index 0 in my string. This is the index 1. This is the index 2 of my L string. At the moment where I compute this, this creates a cylinder for the f equals 0. Then, okay, maybe I should put this brackets. Then this becomes 2. This becomes 3, 4. Okay. So I have a cylinder. I have a pétiole, a leaf here, and then another cylinder here. Here, to compute the light, this is a mesh with triangles. So I need to go through the mesh thing, so in the lscene, to compute the light that will coming on the mesh. But once the light is computed on each triangle of the scene, I need to sum up all the triangles and the light that came on the triangles for the object, for this blade, okay? And then to send this back to the original lstring. But how can I send it back if I don't have the mapping? See, I don't keep trace of the mapping. So I need to know that this cylinder was coming from this A. So I need to know that this leaf blade here, was coming from the ID that called this leaf blade. And so this is a mechanism that is hidden for you, and that you can get, that you can access by looking at the ID in the shape module when you list all the elements of the lscene. So it's a way to map back the lscene to the lstring. It's a mapping back. It's a backward mapping. Okay? And in this way, you have a two-way correspondence between the deep structure of the system, the model, and the surface structure, that is the geometry of the system. I can go forward. So going forward is applying these rules. And I can go backward. Once I have computed something for the blade and the pétiole, I can retrieve the ID that created this leaf and this blade and give back the value in the L rule by using the right index. And then you would have an example here, explained here. Is the basic of this more or less clear, despite the tiredness of everybody?
And you were mentioning the light. Light is not in the lscene.
Light would be external module. No, lscene, actually lscene you can consider that is a set of objects that are meshes. So as soon as you have your lscene, you can use algorithm on meshes to compute anything. So you can cast light on the meshes. You can, you can use different types of algorithm to compute light. This will give on each triangle the light, and then you can get back upwards, back to the lscene first, and back to the lstring after that. And actually, there is an example. There is an example of this. I can show it to you now. Show you this. So this is a plant that is growing, and that will intercept. So you see the light. Okay. So there is a bit. There is let's say a sun at this position, and the plant will be growing here. And there will be this type of mechanism where the lstring will produce leaves. The leaves will be transformed into meshes in the lscene. Meshes will be given, this meshes lscene will be given to an external module that is able to compute the light intercepted by each leaf. And then the light intercepted by each mesh or each triangle in the leaf will be sent back to the lstring, and the lstring will compute its growth according to the amount of light that each leaf receives. So there is a feedback between the environment and the leaf. And this is the way it goes. Okay, so you see that on the side of the light, the leaves that are less shadowed by the others are growing bigger oops, sorry. See, on the side of the light, the leaf in red, they have received more light, so they are getting bigger than the leaves on the other side. Okay, so this is an example where you have so you have the lstring stuff, the lpi, that takes care about the growth of the plant, and it interacts with the external model that makes it possible to compute the amount of light intercepted by each leaf at each step of the simulation. And the example is given. It is in the 4.2 directory, and it is called for the moment 17 diffuse light interception. But maybe you don't have it right now. I will give it to you tomorrow.
We have it.
You have it? Okay.
And what is the model for photosynthesis?
It's simply a light use efficiency curve, which means that that you have here. Okay, it's modeled by a curve, which says that according to the amount of light, the leaf will be able to use a certain part of this light to transform it into carbon, and it's saturated. So it's a typical kind of transformation law that transforms the light received by a leaf into the amount of carbon available to the leaf. Okay, so I have a couple of notions left. So this is important. It is the context sensitivity, the use of context sensitivity. How do I take into account the context within the L system? If I want, for instance, an A to be rewritten as a B, but not every time. I want to be rewritten as a B only if on the left side there is a B. If on the left side there is an A, I don't want it to be rewritten as a B. If you think, this is a way, starting from this axiom, to propagate a B all the way through. Because I will write this, a B will stay a B, because nothing is defined for a B. An A is in the context of a B, even if the A is a branch. It is on the left context of a B. It just touches a B on the tree. So the A touches the B, so becomes a B. This A also touches the B, so becomes a B. Because this A and this A are respectively this one and this one. So they both, on their left context, have a B. So at the next step, the signal will grow up in this way. But now, this A has a B on the left context, and this A as well. So at the next step of derivation, it becomes B. Okay, so what you see is that the signal is propagating from the bottom to the basis. From the bottom to the top. Okay, and these are the derivation that we made. So you have this in the example.
So we had this previously, in an example, I don't remember where, this sign of
less.
Yeah.
Yes, less than. So this is the way to indicate context. You could have this also on the right-hand side. This would indicate context on the right. And you could have both on the right and on the left. So this means that, and you could have simple context or more complex context. I will show this to you so that you know that it exists. That makes it possible to create more complicated rules.
in your rhythmic growth with a delayed acrotonic, so you had this kind of rule with a minus. And I could not understand it. So okay.
I didn't explain, so it's normal. But no, indeed, you are recovering for this. Okay. Now, as you see in the previous example, I need to apply a certain number of derivation to get the signals through the plant, to the entire plant, also to the entire tree. Okay, I need to apply one derivation, then second derivation. So if you have a big plant, you need to derive for a very huge amount of time. And what Przemek, Prusinkiewicz, and colleagues did is that they realized at some point that the propagation could be made on the flow within a computation step, a derivation step. How it goes? It goes in this way. So here I am using the right context instead of the left context. So it goes in this way. If I start with a B, I will start to translate this, to apply my rule, but the B I will read my chain in this way. Sorry, I will read my chain backward in this way. I will start by a B, so there is a possibility to indicate to the system to read right ways or left ways. Okay, so here I indicate to the turtle to read backward. So I start by a B, and then I find an A. A bracket, an A. So B bracket A. Okay, so this is not modified with respect to the origin string. Then when I have this B and this A is in the right context. As to its right, this A as a B. So instead of waiting for the next computation, I do it again. So this was not changed. So the B and the A are here exactly as in the beginning. Now the B here, the A that was here, this one. So this one can be transformed according to this rule, because in the right context of this A there is a B. So I go exactly as before. Now what will change is in the future, because now I can read the A, I have my B, so everything is okay. And now, instead of waiting for the next step, and instead of looking in this axiom, I will look in the lstring that is being built at the moment. So instead of looking in the original lstring, which is this one, I will look in the string that is being built at the moment. And in the string that is being built, which is here, the string that is being built. You see that the B, this A, that would occur here, is in the right context of a B. So I can transform this faster, and I don't need to wait for further derivation before I get to the final result. So actually, this is one derivation step, and then I can see how the signal can propagate in one derivation step. So this is why it is called fast. It was called actually this fast information transfer. Okay. Actually, I skipped a slide where the same thing was explained.
So this fast propagation is due, so you indicate it with doubling the minus or plus sign.
Yes, so when you double the sign here, it means you want to apply the fast rule instead of the simple rule. Okay?
But then so can you do it in both ways?
And you can do it in both ways. Actually, this example is in this way.
Okay.
Yes, but can you it both ways on the same step?
No.
Because it seems to me that there will be some contact with parallel.
This is true. This is true. So what you do is that you split your derivation step in two, and you make a forward step first and a backward step then.
Okay.
But it may be that is not commutative.
So it's two, maybe three, because it just means that it's quite particular in the sense that usually rules are meant to be applied in parallel. but not those ones, I guess.
Yes, here you start to play with the system, because what you do, and let me put it in a bit different way. If you want to conceptualize this in your mind, so we are in the context of morphogenesis, and I have an object. Let me represent this object by a sort of table, like this. At time t, what is safe is to compute the object at time t plus 1, t plus delta t. Each computation of each cell of the object should depend on things at time t, because they are fixed now. Okay? So I don't make any problem here. If instead of this, I start to say computation on this depends maybe on some aspect of t, but also on some aspect of the same time, like this. This starts to be a bit more complicated, because it maybe there are loops here that makes the system impossible to solve. However, there are smart ways to do this, and many of the integration properties that you can find in solving a differential equation, many of the solvers, they work better if you do this in this way. But you need to make sure that there are no inconsistent loop in this system, because this value may depend on this one, that may depend on this one, and then you would end up on a tricky loop. Okay? So this problem in general is conceptually, it's much easier to think it purely forward. So this is called Euler forward step, than to consider it with the possibility of taking values from the same object, because you would need to solve either some system of equations to find out the system, and maybe sometimes the system can be ill-formed when there are loops in the system, and then you would need even more complex strategies to sort this out.
Okay, and then for L5, how is this problem solved? Is it first the parallel growth, then forward, then backward?
You can design this yourself. You have primitives that you can change, and that makes it possible for you to make a forward loop to specify whether the next step is going to be forward or the next step is going to be backward. And then you can combine this in any way. And for instance, what I was explaining yesterday, I think, when we compute the bending of the branches, there were the torque, you remember that I was explaining? Yeah. Then the torque are propagating backward first, and then the displacement are propagating forward then. Okay? So you can get your bending in two waves of information propagation. Okay. You may say, oh, but this is never used, this type of thing. Actually, it's not the case. So this is a case where you have forward and backward propagation. So I just keep this because it's the end of the day, and we need to be a bit softer. But you have the examples in the practicals. But this is the way, the context sensitivity is a typical way to solve this type of problem, like the heat transport problem, where you have a medium where you have certain initial temperatures, and you want to see how the temperatures, you let the system evolve, and you want to see how the temperature will evolve in the medium, and they will evolve according to a heat equation. And the heat equation says the change in the temperature at each point of the bar will be the result of an averaging of the locally of the temperature, of the neighbors' temperatures. And because of this notion of averages on the local neighbors, you need to get this sensitivity because you need to apply a rule that takes into account the neighbors. Okay, so you have, this is intrinsically a context-sensitive stuff. So the idea is to discretize this equation, to write it in a discretized way, and then to use it to express the LPI rules. And this would be explained in the L system rule by context sensitivity. So again, we don't enter into the details. We can look at this maybe tomorrow when we go to the projects. We can pay some time, or if we are more interested, we can pay some time to analyze this example. Okay? It is possible to make more complex pattern matching for the context than just trivial A or trivial B. You can match a full subtree in your structure. So here I was trying to explain how it goes. If I have a string, I can use this rule here that would transform each S in a W. I could use the S in the right context of A, and this would transform each S here that is in the right context of A in a W. So for instance, this S would be transported in a W. But this one would not because there is no A on the right. Okay? So this would result in this string. I could transport each S that is in the left that has as a left context a square as a W, and then you would transfer this one as on the left a square bracket, so it will be transported in the W, etc. And then you could transport each S that has both a bracket and an A bracket on the left and an A on the right, and then you see that there are only this one and this one that are in such situation. So you see that you can combine the things and have a filtering effect more complex. And this can be also done by filtering motifs, full motifs. So I have an S, and I want to say that I will rewrite this S if there is this motif on the right and this motif on the left. So if I apply this to this plant, if I apply this motif that is selected by, that is this one described here, to this plant, I find it twice, two entities that respect to this. This one, because this one has one module, two modules before, so this one's, and this small tree on the right, which is this small one. And this one that has the small tree on the right, and two modules on the before it on the left. So you see that you can combine the things and make them very much complex in a way. Not complex just for fun, but complex because your model, your system is a bit complex. Okay.
But sorry, in your previous example, there were two S's on the main axis, so there was a bracket before.
It doesn't count the bracket? Like the red of the second?
Like the highest red part?
Yes.
I agree that there are two S's before.
Yeah.
But there is a bracket for the branching here.
Like before. I would say that there is nothing before because it's on the main stem. It's not on the same branch, no?
Yes, but here I don't say that this means you remember when we have the signal propagating, it doesn't count the bracket.
Okay.
You remember this?
No, I missed this.
So if you have a branch like this, this one and this one, on their left context, they have this one.
Okay.
Both of them. Even if one of them has a bracket, because the left context is defined independently of the bracket itself.
And even if it has a bracket random stuff. If there is two S's before, it's enough for saying that it's in the context.
Yes, exactly. Yeah, this is what occurs actually here. No, but well, it was an example that I removed, but yeah.
And then, if you would like to use the context to define just the first node of a branch, how would you do this? Like that, basically the left context would be a bracket.
There is the possibility to say, actually, in the current system, there is no option for doing this. So what you need is to filter out the solution, and the last solution would be this final, okay? But we discussed with Frédéric, and we will make something like a star or whatever, or none that would indicate that there is nothing here, because it's lacking. I mean, we are always circumventing this with other finding tricks to do it. So it should be in the So last aspect of this context stuff that is very useful. If we had to enumerate, because the point is that if you do this, you have to enumerate all the context that could correspond to a certain situation, and that could lead to write one rule, to write one law, to duplicate many times the rule depending on all the situation of context that may occur. Okay. So for instance, if I have in a tree, and you will see, if I have, I want to pass an information from here to here, but I want also to pass the information from here to here and here to here. But I will also to pass the information from here to here to here to here. So it's always the same idea. I want to propagate the information backward, and maybe make so if there is a variable x here, I want x on the I, so x1, x2. Here I have x1, x2, x3. So here, what I want to say is that the value x here will be the sum of the xi. Okay? I just want to say this. But you see, if I have to express all the different combinations of these situations, it may be combinatorially quite difficult. So for this, we have this type of construct that says, if I find in my right context many branches from a number I to a number j, minimum number I to a maximum number j, I will consider that this module matches all the set of branches. And in this case, it will be, let me see here. I don't think I have. If I match more than one module, the z value will not be a single value, will be a list of value. And then I can recover in this case. So if I write here, I write something. So these are the S. They have an X. They have an X. So I have S of X, which is in the right context of xi, which is this module multiple times, parentheses, S of Z. I close the parentheses, and I put I don't put any values, meaning that any number of modules is okay. Okay, I write this, and it means that in this case I don't need to write many rules. I need to write only one rule, and when I get the x in the production rule, so this will be the rule here, and then what I can do is do something like this. Variable a is the x, which is the value that is currently stored in the lstring at this position, plus the sum of z, because z is a list of value corresponding to the x. Z contains x1, x2, x3, all the variables that have been gathered together into a list. So it's a bit syntactical stuff, but it makes it very easy to write propagation in a branching system. Because it's a problem. How you write propagation in a branching system. And finally, and this is the last point of the day, last slide of the day, you can use it to propagate information and to solve the heat equation in a branching structure. Not only in a bar, but in a branching structure. So maybe I can show you this. So this is the one. And you see that if I show this, rewind. Okay, so this is a tree. Well, a small tree. I gave heat high temperature to the extremities of the tree, and I want to solve the heat equation on the tree structure. So I didn't change anything about the rules. I just changed the way, the context sensitivity by writing this type of thing. And now you see that for almost nothing, you will get the transport equation that is solved on a tree structure. And I could make the tree as complex as I want. It will still continue to work. And so you have a sort of extension of how to solve the equation on a tree structure by using this possibility to propagate information back and forth in the structures using context sensitivity. Okay, questions? Tiredness? Yes. Okay. Well, thank you very much, everybody. I think we can resume tomorrow. I think tomorrow will be about integrating things. And we are very close to having a sort of a basic understanding of how to construct the plant structures at an integrated level.
Thank you.
You're welcome.